Hello everyone. So I'm going to be talking about some hardware trace features and why they're useful and some of the challenges with them. I'm going to use examples from ARM because that's what I'm familiar with. I don't want to talk about other architecture features that I don't fully understand or might misrepresent, but I think one of my themes is going to be actually all architectures have this kind of feature. They're available for other vendors as well. And I think one of the challenges is how do you bring consistency to that and actually deal with the fact that all these things have got features and they do it in a slightly different way, and we need to make it useful for end users by bringing some consistency through the tooling. So everything I say about ARM is probably applicable to other systems as well. So the basic problem, visibility into software. We want to know what's going on. We want to know what's the cause of performance issues, particularly sort of where it gets low level, if you've got device drivers, if you've got real-time code, if you've got code that's sensitive to, say, microarchitectural effects like things missing in cache and causing a performance issue. You want to get some detailed information out on these performance sensitive areas. So we've heard a lot about software tracing features, very powerful features, very rich set of software features. You can have sort of compiler-generated features. You can instrument your code. You can have features that can instrument production binaries, either by sort of patching the code or by running them under a DBI tool like DynamoRio, which we use. DynamoRio, it's a very, very good tool. We use it for lots of things. And this is a very sort of rich environment. And you can do loads of things with these tools. But these tools do have a probe effect, and there are cases where once you start instrumenting the tool, once you start getting the CPU to execute an alternative code path, you perhaps are obscuring the problem that you set out to solve in the first place. So for specific kinds of problems where you are interested in these kind of low-level performance effects, where you're talking tens of cycles, you want to know where your performance is going. Once you start putting software instrumentation in there, you start disrupting things. I mean, timing, obviously, because you're executing more code, but also you're affecting the cache footprint. You're executing more code, you're pulling in data, perhaps you're writing to a ring buffer. That can all have an effect. It can, in some cases, perhaps cause the effect that you were looking for to go away. It may also struggle with code that is hard to instrument. So in some cases, you just want to see actually what is happening on the hardware in the original code. So ideally, you just take your whole system and you run it in an environment where you can literally see everything that goes on. And surprisingly, we can actually do this. So there are basically two ways. You can either run it on an extremely expensive hardware emulator, and you get a whole load of signals out, and you can run it through a trace processor and sort of reconstruct the state of the software. Or you can do basically the same thing in a simulated environment. And that is incredibly slow, but it's possible, and it is exactly what people do when they are investigating problems at the hardware level. And I think it's important to remember that at some level people are doing these things. So it may be a very restricted set of people, but these things are feasible and they do happen. So it's always useful to be able to isolate performance problems to a point where they can be run in these environments. And you can then sort of reconstruct them in this environment where you can bring something up in a simulator. But obviously this is not something that ordinary users can use for application performance problems, or even the average kernel developer wouldn't have access to this. And even the people who do, I mean, it is incredibly slow if you're bringing stuff up under simulation. So we're really looking for things that can be much more practical and give us feedback on what's happening on real hardware. So there are things like hardware performance events. So they're basically sampling based. You can basically interrupt the core every a few microseconds and sample the PME events. That's good, but it's generally aggregate counts rather than detail. You can potentially virtualize your environment into something that can give you a performance model. So you could perhaps model the cache in TLB and replay your code through this. And that can be really useful. It can sort of, if you've got effects to do with, say, your data layout, then even if you can't work out what's going on hardware, running it through some kind of cache simulation will be a lot faster than logic simulation, and it may give you really good insights into why you're seeing performance problems that you are. And then there are sort of full system performance modeling environments, sort of widely used in architectural research, but they tend to be less practical for the average application developer, partly because they don't tend to be complete and fully featured. You can't just boot up Linux and expect everything to work. So we are still perhaps looking for things that get you feedback on what's really happening in hardware. So this is where we get to processor trace, which is a feature on several different types of CPU. ARM calls it ETM or ETE, or in the past it's called it PTM. Intel has a PT feature. This is basically a trace of what's going on the core, particularly instruction trace. And it's very, very highly compressed. It's basically trying to minimize the bandwidth of the trace coming out of the core. So you will basically indicate each branch direction with a single bit if the decoder can be assumed to have access to the original code and then reconstruct the way that the control flow was flowing. And this has a lot of impact on how you actually use these tools in practice, because you are getting something that is kind of making assumptions about the decoder having access to the original binaries and having access to kind of metadata about where these binaries were loaded into the address space and when they were loaded in. And when you get things like JIT and self-patching code, you basically have to communicate this to the decoder somehow. Obviously, all performance tools that sample program counters, and even things like last branch record or PEBs or anything like that samples a program counter, even interrupt-driven program counter sampling, if you've just got a 64-bit program counter, then sample at some point in time on some system, that you've still got the problem of where did this come from? What was it in a dynamic library? Was it in somebody's code cache? If you've got the source for the code, is it actually what was there at runtime, or has it been patched? So you've always got that problem. But with this hardware trace feature, it's kind of like a double problem, because even to decode the trace and follow the series of the program flow, you have to have access to the code. So in very early days, program trace was mostly a sort of off-core feature, an off-board feature. You basically attached a big trace capture unit to your device. People still use this. Even production devices may have some port somewhere that you can break out to consume the trace and harvest it in something with an enormous trace buffer. So this is still something that's done. But if we're looking for tools that are usable by the end user, we're looking at sort of how to do this thing on chip, how to generate the trace and consume it on chip. So ARM has for a very long time had something called Coresight, which is the sort of on-chip trace management fabric. And this is used to kind of route trace around the system. So each core will generate trace, some other things can generate trace, and there's a sort of internal trace bus that's dedicated to trace. And one thing you can do is push it out through an external port. You can also collect it in a dedicated buffer, and it will go into the buffer, and you can then read it out. And we can use this from software, self-hosted software. So you can basically collect your trace into a dedicated buffer and then read it out. The buffer tends to be extremely small, so it's actually not very practical to do this for significant amounts of data. So systems more recently have had an embedded trace router, which then routes the trace back to memory, and this is generally what we use for self-hosted tracing on devices these days. So if you've got somebody who's using perhaps perf tools or AutoFDO to collect trace, it will generally be using this system where the trace is coming out of the CPU, it's being routed over the dedicated trace bus to the embedded trace router, which is writing to a memory buffer. And the Linux device drivers take care of all this. More recently, ARM has introduced a sort of alternative way to do this, which is more CPU-centric and certainly more software-friendly. In this new setup, each CPU has a dedicated trace writer. So the trace will come out of the CPU and be written directly from the CPU, each CPU, to the system interconnect, and then through that to a memory buffer per CPU. The actual trace generation, trace format, is pretty much similar. And Linux does a heroic job of basically trying to make this and the previous way look very similar. So at the perf level, things should just keep working. Internally, there's a whole lot of engineering being done by some, a lot of really good people to handle the differences between these two ways of doing things. Being software-centric and being CPU-specific, it means that the trace context can be managed as part of the thread context. And this makes things a lot simpler. So the trace environment can be managed and swapped out just like, say, the PMU configuration or anything else that's part of the CPU context. So a lot of things become simpler, a lot of things become less hardware-specific. But this is relatively new. So on hardware that you've got now, or if you've got ARM hardware, if you're collecting a hardware trace from phones now or other devices, you'll generally be using it the old way. And the Linux device driver framework will be handling all that trace routing. So what is trace good for? Well, it can get you visibility at the per instruction level, or at least sort of down to the level of individual branches. So you can basically reconstruct control flow completely. You get some timing information, and it can be useful to do various kinds of analysis that rely on reconstructing control flow. Things like coverage checking, profiling. There are various tools out there that have used processor trace, either from PT or from ETM or both, to do interesting kinds of malware analysis, CFI, fuzzing, and so on. Another thing is postmortem. So people have been setting up hardware trace to capture into a ring buffer. So this is an operation through the lifetime of the device, and then if it crashes, this is then uploaded for analysis. So you can see basically what was happening, what the software was doing for the last period of time. So if you want to sort of get a feel for what you can do by visualizing trace, this isn't actually a tool that you can get. This is some visualizations that we did internally. But you can see that we're using processor trace to look through the critical path in a kernel routine on two different implementations. So you can see that basically the path being taken is the same, but the timings are different. So you can get a feel for how the different implementations handle the same code. And you can see basically what it is that's perhaps causing these time differences. So we can we don't necessarily get visibility at the level of so-and-so instruction is taking 10 cycles, but we can get a really quite good picture of where basic blocks are taking time, where individual functions are taking time, and how this is sensitive to the particular situation in which they're being used. So, how would you use processor trace on Linux now? It's a lot easier than it used to be. It's all now handled by the Linux driver framework. The actual command is going to be vendor specific, or it's going to be architecture specific. So the event is not yet standardized between, say, the ARM environment and the x86 environment. It could be, potentially. I mean, it wouldn't be a major step to standardize the name of the event so that it just said capture some trace, and then the tools handled the differences in the trace format. We haven't yet gone to that step, but it is a very logical next step. And then there are various ways to kind of control and filter the trace. You get the usual, you can say user space only, you can set address range filters and so on. And then the kernel will set up everything to collect the trace. And then you just run the workload, and you get a aux buffer full of trace. The trace is, as I say, in a highly compressed format. So if you want to deal with it directly, you can convert it into a set of basically program counter samples using perf inject. But for any kind of heavyweight analysis, it's probably better to process it directly. So there is an open source trace decoder. Again, there's one of these for Intel as well. And then you can feed it into visualization tools, profiling tools. So there's a flow from processor trace into AutoFDO, which then generates profiles for GCC and LVM. And that can be then used to optimize software builds. So going into more details on decoding. So decoding needs information about how the trace was configured. In perf, this is all in the perf record aux trace info. So there's some metadata there which explains how the trace source was configured so that you can decode it. You need the images for the code. So for things like dynamic libraries, this is all handled with mmap records. For patching code that patches itself, certainly in the kernel, there's now a sort of text poke record. This is relatively new, and the kernel can then basically notify any consumer that the code has changed. And of course, you need to keep track of things like context switches as well. And again, all that's handled through perf records. So there's a process in any trace consumer of sort of matching up the hardware trace with the set of time-stamped perf records, so that the hardware trace is always decoded in the right context. And this is all left to user space. So the kernel itself does not attempt to decode any trace. It doesn't process the trace in any way. It just returns the entire buffer back up to user space. So any user space tool basically has to go through this same procedure. I think this is a real candidate for sort of libifying in user space, so that there would be a standard library to consume the trace. As I say, you can do this with perf inject or perf script, but it tends to blow up the trace massively, and I think that there's a big gap here for some better tooling. One interesting feature is that you can, to a limited extent, trace hardware performance events. So you can actually connect the hardware performance monitor unit to your trace unit, and the PMU is monitoring things like cache miss, branch mispredict, and so on. And you can feed these into hardware trace. You only get 4 bits. I'm talking. This is ARM specific. You only get 4 bits, and it is very loosely timed with respect to instructions. But even so, it's a lot more kind of finer grained than PMU sampling. So if you're doing something like perf record with a sort of event-driven sampling, you might get a PMU sample, perhaps every 100 microseconds or something. With feeding PMU into trace, you get it much more closely aligned with where the effect is happening. And so you may be able to match it up with the code that you're seeing in the trace. This isn't currently exploited by perf tools. I think partly because there is no, in terms of what you're asking perf to do on the command line, there's no conceptual mechanism for saying, well, let's ask for a PMU event and let's ask for trace and then somehow connect the two. But it's certainly something that could be supported. So I've got an example here. I mean, one of the earlier presentations mentioned the sort of the VDSA routine to get the current time, and the fact that this was kind of performance critical for anything that was using, clock get time to timestamp a trace event. So we can use hardware trace to see exactly what's going on here. I'll blow this up because if you can't see it. So you can see that we are tracing basically the call into the C library and then the call into the VDSO, so we get the exact sequence of instructions being executed, and we get cycle counts on the branches. So you can see here that generally you are executing instructions at a high rate. You might execute 4 instructions in 2 cycles, because this is a high performance superscalar core. But there are certain things you have to do when you are collecting the timestamp and correlating it with the kernel's kind of time conversion parameters that mean you have to issue serialization. And you can see there that actually this is quite costly. And this is why doing things like collecting the raw timestamp data and then doing the correlation as a post-processing step save you so much time. And you can see there that the trace has been annotated by feeding in the PMU event that shows you've issued a serialization barrier. And this one isn't particularly useful because you can actually see the ISB in the trace as well. So you don't gain much by feeding it in as a PMU event. But if you had something like branch mispredict or TLB miss, then feeding it in as an event into the trace can actually get you some insight roughly about where this is occurring. So I think this is a powerful technique, and it gives you a level of insight into where you're spending time in your code that is very hard to get any other way. There is an alternative way that gets you, in some ways, similar information, but a totally different way. So we call it statistical profiling. There are, again, similar features on other architectures. So this is a feature that's come in relatively recently. Tends to be on the higher end systems, server systems. And that samples individual instructions and collects microarchitectural data. So it collects things like the timestamp and what kind of instruction it was, where it was, what address it was using, did it suffer a cache miss, TLB miss, and so on. And you can get very sort of data-centric analysis. I should mention that processor trace doesn't sample any data addresses or values. We can do that for embedded systems, tiny embedded systems, but not for the mobile and server cores. So if you want to do any kind of data tracing, SPE can get you that kind of insight that you wouldn't get from processor flow trace. So SPE can tell you about individual instructions, how they're interacting with the memory hierarchy. You can do some filtering. You can filter the samples based on the events they encounter. SPE is attached to each core, and it writes out to a memory buffer. So it's very similar to the new style processor trace. Different buffer. So Linux is managing 2 buffers, one for processor trace and one for SPE, if you've got them both enabled. But also, I mean, they're both coming up through the perf subsystem. And SPE also comes out as an aux buffer in perf. So rather like processor trace, it's coming out as an aux buffer. And then you decode it in user space. And perf tools have good support for this now. So there is an event, ARM SPE. You can open it as an event. But there are so there is a limitation that you can't use this in the same perf command with ETM. That's not a hardware limitation. It's not even a kernel limitation. It's just, I think, because of the limitations of the perf data format and the fact that aux buffers have to be aligned with one particular trace type. So this is an area where I think we're kind of stretching what perf can do. I've tried to work with the perf user space tools, and it's so complex. I think we're running up against the limits of what we can do with the perf data file. So perf, as I think Arnaldo mentioned on Tuesday, SP is now exploited by the sort of memory-centric perf analysis. So things like perfmem and perfc2c are using SPE to do things like a breakdown of memory latency, which levels of the memory hierarchy data is being fetched from, are things missing in cache and so on. And one question I think is when I use a system, what will I see on that system? How standard is it? Is this a standard feature that's available everywhere? Or is it going to be very, very implementation specific? And I think with all these features, even things like performance hardware events that we're used to, some bits are standard and some bits are very implementation specific. And again, this is not specific to ARM. It's something for all vendors. There are things that are totally standard and ubiquitous and standardized across all implementations, and some things which are very, very model specific. So sometimes you have to find out the model number through CPU info. You have to find out the implemented architectural features through CPU info or HW caps, and just sort of dispatch on those and say, what have I actually got on this specific target? I think as different implementations proliferate, as different vendors come out with different models, keeping track of these things is very difficult. And so anything we can do to bring standardization or discoverability to there will make life easier for software. So this is where I'm sort of finishing up. Hardware trace is very powerful for specific kinds of problems. It can give you insights into things that are very hard to reach by other means, at least on sort of ordinary hardware. But there are some challenges to it. And I think some things where sometimes the challenge is fundamental. There are fundamental limitations where you can do this. But other times I think it's that we perhaps need to work together a bit to work out how do we make this more usable? What are the problems we're really trying to solve? Can we come up with common solutions? One of them is security. So the more you go into the low levels of what's happening, the more you run up against kind of both sort of new potential things can go wrong. So are you leaking stuff? Are you able to expose, I don't know, levels of the system, enclaves of the system that you shouldn't have access to? Any of these features you have to sort of make a security case for. And this is a very practical problem. It particularly affects people like cloud service providers. If they're providing these features in a VM image, they need to know they're not exposing their other tenants. And if you go to any of these cloud service providers and say, what perf tools have I got? Have I got PMU events even? You may find they aren't there because it has been hard to make that security case. And so when we design these things now, we have to design them on the basis that the end user may have very, very limited access to the system. And even the kernel may have very limited access to the system and will be running in an environment where the kernel itself is seen as a threat. And something has to stop the kernel, the perf subsystem in the kernel, reaching into areas where it can't go. Another problem with hardware mechanisms, they tend to be sort of single use at a time. So they're monitoring something on behalf of some agent. And they could be tracing something or counting something or anything else. But they tend to be single agent at a time. So for example, you might get an application developer trying to profile their workload at the same time as maybe like some system administrator is finding out what all the applications on the system are doing. And then maybe at the firmware level or the hypervisor level, the the OEM is trying to do some kind of tracing and monitoring for crash recovery, post-mortem, even something like power management or intrusion detection or anything like that. And all these things kind of conflict. They try and it may not be difficult. It may not be possible to do them at the same time. With PMU counters, we can kind of finesse this by multiplexing them. So I mean, you'll know that if you open like 100 PMU events, the kernel will time multiplex them through the however many counters you've got. It's usually about 6 or 8. So you can do that. We can sometimes split PMU counters between, say, the hypervisor and the kernel. So the kernel may boot up and find it's only got 3 counters because the hypervisor's got 3. With other features like trace and telemetry, it's harder to do that. Even with things like uncore PMU, it's harder to do that because there is just one thing that needs to be programmed, and it may not be attached to a thread context, so it's not something you can time multiplex easily. So all these features, I think it's something where you may need to sort of arbitrate the use between different agents. I'm not sure we have a good solution for that yet. Virtualization is a challenge, both at the sort of like the technical level of how do you make things keep working when there's 2 stages of translation, but also the sort of security issues where your tenant operating system may not be fully trusted by the host. Software and tooling. I mean, we've seen some great tools this week. We've seen tools that sort of can handle very large traces of basically events. I think one of the challenges is, can we scale down to the nanosecond level? And we can scale up to the level of hours and perhaps days of traces. But what happens when you go down to nanosecond level trace? Is there a smooth experience? Can you drill down into, say, some jank in some routine somewhere and start seeing individual instructions, or perhaps the summaries of lots of executions over the same instructions based on very detailed hardware trace? And I'm sure we can. I'm sure that there's nothing stopping us doing that, but I think at the moment we haven't yet reached the point where the tools can simply harvest this data. And of course there's the variation I mentioned. So I think we're now at a point where we get implementations providing quite similar features, but we have some work to do in the tools to make these features look the same. So where you can just say perf record hardware trace, instead of having to use vendor-specific event names. And then there's uncore, which is even harder to standardize, and where you are much more reliant on going to some data sheet and saying, exactly what's going on in this chip and how do I get telemetry from it. But I think all these challenges are things we can meet, and all of them will help us give better performance insights to people in the future. Well, thank you. That's all I got. Any questions?
Cool. Thank you. Okay, thanks. I think we've got lots of questions. Okay, so we'll start at that end of the room, and then we'll come here, and then back. Okay? So I think they're on the yellow mic.
Hello. Yeah. Hi, Al. Thanks for the talk. It was really interesting. I've got a comment, a complaint, and a question. I'm to your right. There we are.
All right.
There we are. Yeah, so the comment first. So the VDSO code you showed with the ISPs and the read of the timer, I have an optimized version of that code, so I'd love to see a side-by-side trace to see if the optimized version is any better. So maybe we can sync up about that.
Yeah.
That'd be cool. Complaint is, I mean, it was evident in your talk that there's the TRBE, or ETE, and there's SPE. It's a real pain for systems developers to have to deal with, bespoke programming interfaces for all of these devices. It would be really lovely in the future if tracing hardware could be exposed in one way, so that, for example, the difficult virtualization work that you have on this slide, we wouldn't have to redo it for every single device. Right now, SPE, for example, is barely virtualizable architecturally. And assuming that gets fixed in the future, well, who knows if ETE will be fixed at the same time. So I'd really like to see, for future hardware, some consolidation of the programming interface. That's the complaint. The question, One of the motivations that you gave for hardware trace compared to software trace was to reduce overhead, the impact of the tracing on the system. But then when you showed the TRBE, it used virtual addresses and it plumbed into the memory system as well. So to what extent can things like the page table walks and cache allocations be controlled for those pieces of hardware trace? Thanks.
So good questions, and people do ask about the effect of the memory streaming coming out of the SPE or TRBE, or even the ETR on the overall kind of system performance. These things do tend to bypass the cache, or at least bypass level 1 and level 2. So they're cache coherent, but they will go directly over the bus. So for example, SPE will write out directly, it will write out 64-byte transactions directly, bypassing the L1 and L2. And then L2 will, if necessary, snoop back from the SPE buffer. So does that fully...
Well, it's the things like the TRBE, for example. Is it possible to lock TLB entries for it? I mean, how software controllable is this? If I really want to minimize the impact it has on the system, do I just have to assume that it's been designed in a way to have minimal impact, or can I control that to someone?
I think that's partly a KIRO, I think. I mean, your operating system and your hypervisor could both lock this into memory with a huge page, and that's probably a good strategy. So I mean, if your hypervisor is being friendly to your OS, it will probably allow it to pin a huge page into memory, so that you'll have that translation there. And I don't know whether you can fix the translation in TLB, but
there is a related problem. I've got a friend, I'm not an Intel, but a couple of friends of mine are, and they note that one of the problems with Intel's lower level push to traces, and one of the reasons where they use external hardware for a lot of them still, that if you turn all the trace on, it will completely drown the memory bus, and there's no bandwidth left for anything else. It will completely wreck the timing of whatever it is you're trying to time. And the more you trace, the worse this will happen. So I guess in the end, you'll need filtering before these things hit memory.
Yeah, I should say, I mean, if you are harvesting trace from every CPU at full speed, you are going to swap your system. So in practice, you would need to do perhaps some kind of statistical sampling. So you could use like a subset of the CPUs. You can do address filtering. You can do what we call trace strobing. So in fact, the ETE hardware, you can actually program that with what's like a state machine with countdown timers, and it will sort of pulse the trace on, capture a random window, and then turn it off again. So you can actually reduce the bandwidth, and of course you could do that at software level as well. So some of these like automatic profiling systems, they will turn the trace on for a very brief window, a couple of seconds every few hours, to harvest the trace. So it's not like you get it running full speed all the time. But of course, then that means that if you're using it for something like the post-mortem debug use case, the flight recorder use case, you can't do that. I mean, if your flight recorder wants all the trace from all the CPUs all the time, then you have to set up your hardware a completely different way. And there are people who do that. So, for example, people building safety-critical devices would want the trace on all the time, and they will specify their trace collection capacity to be able to do that. And that's where they would probably still use the dedicated trace bus. So it's really kind of, there's flexibility there. There's the ease of use of feeding it into the main memory system. And then there's the option to use a dedicated trace bus and dedicated RAM areas that are specifically there for trace. And it's just about what your system requirements are. But you're right. I mean, the overhead of trace collection it's not entirely zero overhead, but at least you are bypassing the L1, L2, TLB, which you tend to trample on if you instrument your software with like a call out to a software instrumentation.
Cool. Okay, and I think there was questions on this table. We get the red mic.
Hello. Thanks for the talk. I have a quick question. So you have demonstrated how to use these features on Linux using perf tools. I was wondering if there is a similarly simple way of using the same features on Apple's ARM-based devices, like on macOS.
I would love to know. Sorry,
I guess you can always install a Sahi Linux. But
if anyone in the room would like to talk about that, I'd love to have a conversation about that. But I know nothing about how this, whether this is available on Apple.
No, sure, thank you.
Yeah. Sorry.
Cool. And was there another question in the back? Okay, we'll go there first because they were first, and then we'll come here. Can someone? All right, I'll take this mic, and then we'll come back here. All right. Cool.
Thanks for the talk.
You next.
So to continue the first question, most of my question was answered, but still, if you dump the trace to memory, so you're gonna not only have a lot of memory, a lot of data to handle, but the rate of the data going out will affect the program's performance. So I think there is still a performance effect issue to be noticed here, right?
So I think one important point is that the trace is non-blocking. So if there's any congestion in the path to memory for the trace will be dropped, and there'll be a packet saying, I had to drop this trace because I exceeded the bandwidth. So the core will not be stalled in any way by trace.
Oh, okay. Thanks.
Okay.
Cool. And then question in the front.
Hi. So you mentioned the challenges with JIT and capturing, and you talked about using the JIT cache. But I mean, in a more general case, if we looked at using perf to actually record the memory contents at the time of these events, because I think at the moment it just records addresses and lengths. You still need to capture that data in another way.
Yes, I mean, I think things like JIT dump can capture memory contents. So they will generate like a sort of pseudo ELF file that can then be used by the trace decoder to reconstruct the trace.
But is that something that would work for all JITs, or is that specific to like hotspot? Or
I think as a technique, it's supposed to work for all JITs. I mean, okay. when it was introduced, I think the idea, I think it was like Stefan Iranian or something like that introduced it.
Okay.
And I think the idea was that it would be a standard format that any JIT could produce, and then perf inject would then read them in and use that to annotate the trace.
Okay. Right. Thank you.
But I'm sure we could do better in that area. I mean, there is an overhead on JITs if they have to start generating this metadata. I've kind of claimed that trace is low overhead, but if you're then asking every single JIT, every time it generates code into a code cache, to start building itself an ELF file and then writing it out somewhere, that is then going to be high overhead. That's going to be high impact on trace, on things like cache probably. So I think that there's potentially something we could do better there in terms of perhaps writing it out into a ring buffer and trying to minimize the overhead of that.
Yeah. Thank you.
Okay, I think we have one question next. Anyone else?
So you mentioned the flight recorder idea where you can attach the CPU trace kind of to a process that has just crashed and include it in like a core dump. This is something that the system has to institute at like a privileged system-wide level, correct? Like there's no ability to say filter it down to an unprivileged process. Like the OS would have to know how to do that, right?
You could do it for a non-privileged process. I mean, I know GDB has support for reading Intel PT, so I don't think that works for ARM yet, but in principle you could set up trace as a flight recorder on a user space process and then load it into your debugger if it crashed.
But the U in that case would have to be the kernel. Like the kernel has to know how to distinguish these instructions for this process A and those instructions for process B. I'm sure the CPU doesn't know anything about that, right?
So when you ask perf to open a trace event on a process, the scheduler will swap the trace context in and out, so that the only trace going into the buffer will be from that process.
Okay, it's the scheduler that does it.
Yeah.
Thanks for explaining.
So there are multiple modes. I mean, you can operate trace in the per process mode, or you can operate it in the system-wide mode. And then if you're operating it system-wide, then you have the problem where you get multiple threads in the trace buffer, and you have to use things like context ID or timestamps to disambiguate them.
Sorry for the newbie question. That was really helpful. Thank you.
Cool. Okay. Are there any more questions? Okay. In that case, thank you, Al.